Hello everyone and welcome to OneClass. My name is Jeff Krause. I have a PhD in physical chemistry and today I'm going to run through a few undergraduate level, high school level physics questions. So here's the first one. So it's just to calculate the RMS speeds of nitrogen molecules at 25 degrees Celsius and 125. So this uses the Boltzmann average kinetic energy expression. So here we have that our average kinetic energy, just gonna bring this back a bit here. I think I ended up with a large brush size. Our average kinetic energy is 3/2 kT, where this here is Boltzmann's constant. And this, I'll draw this down again. This here is the temperature. So if you look here, so this is kinetic energy, so this is in joules. So Boltzmann's constant is in joules per Kelvin. And now the nice thing is that K is actually our ideal gas constant times 1 over our Avogadro's number. So that is what cancels the mole out of there. So that's 8.314 joules per mole Kelvin times 1 mole over Avogadro's constant, which comes out to be 1.3806 times 10 to the minus 23. So that also means that we can re-express our average kinetic energy as 3/2, or sorry, let's backtrack a little bit. So our average kinetic energy is 1/2 mv squared, where here it's the average velocity squared, and I'm going to stick the squared outside actually. So our average velocity, or our average speed squared, and so that equals 3/2 kT. And so then our average speed is then the square root of 3 kT over m. But as K is our ideal gas constant over Avogadro's number, then this is just 3 RT over m times Avogadro's number. Which would be in 1 over mole. And so our mass, which is in grams, times Avogadro's number is just our molar mass. So this is just the root 3 RT over our molar mass. So that makes it significantly easier to answer this question. So our average velocity, so given our temperature at 25 degrees Celsius, then that is the same as 298.15 Kelvin. And given another temperature at 125, that'll just be 398. Our molar mass for nitrogen for N2 is 14.01 grams per mole. There's two of them. So that'll be 28.02. But then we need to multiply by a kilogram per 1,000 grams. As we're going to need this to be in kilograms because our R is in joules. So R is 8.314 joules per mole Kelvin. And a joule is a kilogram meter squared per second squared. So for the kilograms to cancel, we're going to need our mass in kilograms. So our molar mass for N2 is 0.02802 kilograms per mole. Okay, so I think we got all our units figured out, and so we can answer this question. So our average speed at 298 is the square root of 8.314 joules per mole Kelvin, 298.15, and all divided by 0.02802 kilograms per mole. And so the Kelvin will cancel, the mole will cancel, and the kilogram is going to cancel with our kilogram in here, leaving us with meters squared per second squared, which is good, because when you take the square root of that, our speed is going to be in meters per second, which is the appropriate units. So if we run this through on our calculator, we get 515.04 meters per second. And if we repeat this now for 398, then we would get 8.314, 398, and all divided by this 0.02802 kilograms per mole. Moles cancel, Kelvins cancel, the kilograms will cancel with the kilograms and the joules, leaving us with the appropriate units and giving us 595.33 meters per second. Okay, so those are our different speeds at different temperatures. So sketch approximate curves of the molecular speed distribution. So our speed distribution, which is not integrated, so it needs to be integrated to give us our actual speed. But this is the number of molecules at a given speed. 3/2 e to the minus mv squared over 2kt. So this is our non-integrated, but it still, as the integral of a Gaussian is just going to give you a Gaussian back. It gives us our basic shape, so it should follow a Gaussian. Our width is going to be proportional to temperature, so as temperature increases, the width will increase, and this is going to be approximately our prefactor, and so as temperature increases, this guy should decrease. So together, even though this is not integrated, we can still get a basic shape by saying while the center of our distribution is going to be at our average speed. So so we're going to have about 515.04, and we're going to have some width, and so we can draw the distribution such that it goes through that. And then at a higher temperature, now these guys are probably going to be sandwiched between each other. At a higher temperature, we're going to have a peak at a lower spot and be a little wider. And so hopefully this looks like some kind of a symmetric Gaussian. And I'm starting to think, there we go. So I think it's a little wider, and it's peaking at a higher temperature. There. So there's my 2 equals 298.15, and my t equals 398.15 speed distributions. So they should be Gaussian, peaking at your average speed, and the higher temperature one should be a bit wider but a bit shorter. That would be an approximate sketch of your molecular speed distributions. Okay, so if we take a look through the solution posted, so it just gives the equation, that's fine. So they get different speeds, but if we look closely, we see they did not convert the molar mass from grams per mole to kilograms per mole, which is going to throw this all off. So your units in the end are not meters per second here. And then they've pasted up some picture of the distributions, which is what you, so these are what the distributions would look like, but so there's a unit error in the calculation. So these are not correct. Okay. So here we have some converging lens. And so if we have our focal point, it wants us to try to draw things as well as possible. And so, and I'm already kind of messing it up, but let's see if I can not mess it up. So I'm going to try to draw this nice and big, like this. Okay, so there's our focal point, which is about 10 centimeters over, and then construct accurate ray diagrams for objects at distances of 20 centimeters. So here's the 20 centimeter object. And so the way we're going to draw this is we can sketch 3 rays. So a ray which goes straight is going to pass through the focal point. A ray which passes through the focal point is going to come out straight, and a ray which passes through the center is just going to go. I was doing well. It's going to just go straight. So, and they should come to the same spot anyway, so that kind of helps your hand. And so because of my my poor drawing skills, then it comes out there. So it wants us to determine the location from the ray diagram. So I mean, from this, it looks like it's, if this is 20 centimeters, then it looks like it's a bit more than 20 centimeters, but I would assume that because of the magnification that is obviously happening on the right side here, that it's going to be at 20 centimeters. Is the image real or virtual? So here the image is real and inverted, right? So it's real because it exists, so we didn't have to backdraw the rays, which we'll see in a second. And it's inverted because, well, it's inverted. So it's on this side, the object is up, on this side the object is down. And now if we apply our equations, so 1 over the focal point is 1 over the distance of the object. And there's a few different ways that I've seen this equation. So it's either plus 1 over the distance of the image, but the distance is always measured positive this way for the object and positive this way for the image, meaning if the image is this side, it'll be negative. Or we could represent it always as positive on this side, and then it would be 1 over d naught minus 1 over the distance of the image. So this sign changes depending on your definition of whether it's positive on one side or the other side. I'm going to use this one, even though it might be a little bit more confusing. So what that means is my d naught will be positive if it's on the object side, which it always will be, but my di will be positive if it's on the image side, which is over here. Okay. So it's purely measured from the center of the lens and going towards the direction where you would expect it to be. So 1 over 10 centimeters is 1 over 20 centimeters plus 1 over the distance of the image. 1 over di is 1 over 10 minus 1 over 20. Giving them the same denominator. So it's 2 over 20 minus 1 over 20, which is then just equal to, so 1 over the distance of the image is 1 over 20. So our distance for our image is 20 centimeters. So again, this will be positive, which it is, for an image distance on the proper side, which is this side. And so the magnification is minus di over d naught, which in this case is minus 20 over 20, which is equal to minus 1. So it's an inverted image. Now this magnification equation will also change depending on which of these two you use. So obviously if your di is chosen differently, then this negative sign will not be there. So if you use a different axis, so this negative sign is particular to the equation I was using. So in summary here, so this is a real inverted image, which if we compare it to our diagram, this diagram I drew here, it looks okay, although I would say it appears as though it's magnified and probably not at 20 centimeters. But if we do the actual equations, then that's where it comes out. And I think I did a pretty good job, but not a great job. Okay, so 5 centimeters. So again, let's draw our lens. And 10 centimeters. And 10 centimeters. So there's our focal point. And now we have our object here. And now we really only have our center ray that we can draw. And our ray which passes straight must go through the focal point. And now these two rays are diverging, so we must back. I think I drew this in a way that's going to make this impossible. Yeah. In retrospect, I'm going to redo this looking at my original figure because this is going to be huge. So let's compress things a little bit. So I'm going to put my focal point there. Focal point there. Object here. Okay. Did I compress that at all? Yeah. Okay. So through the center, straight through the focal point. And so then these two rays, this ray here needs to be back propagated, and this one here needs to be back propagated. And now I've got something that looks okay, but it's probably a little magnified, I think. But that's where it's going to sit, is wherever the two rays converge in the back propagation. And so this is going to be a virtual image which is not inverted, and it's also magnified, right? So if we run through our equations here, 1 over f is 1 over di plus 1 over d naught. Remember that d naught will be positive if it's on the image, or sorry. Remember that di will be positive if it's on the image side and negative if it's on the object side. So here we have 1 over, I'm going to do this properly, 1 over 10 centimeters is the focal point, or 1 over the focal point. 5 centimeters is our image, is our object. And then that's 1 over di, so 1 over di is 1 over 10 minus 1 over 5, giving them the same, was it 5? Yeah, okay. Giving them the same denominators here, so 1 over di is 1 over 10 minus 1 over 5, which is equal to 1 over 10 minus 2 over 10 minus 1 over 10. So apparently they should have converged at the focal point, so I must have just been trying to force it. So I guess it would be here. Anyway, so di is minus 10 centimeters. So it's behind the lens and at the focal point, in fact. So I must have been trying to push it, so I guess it should be there. So now if we do our magnification, minus di over d naught minus 10 over 5, which is equal to 2. So it's upright and magnified. And it's a virtual image because we're on the negative side, or the opposite side that we would expect. And in this case, I would say my drawings are lacking. Mostly because I tried to push it out because I thought it went that far out, but it should have been more like here, which you can kind of see it, I'd say. Okay, so that's roughly how you do this. I'm obviously not the most artistic, but that's roughly how you do this. Okay, so checking through this. So here's our ray diagram. And there's the ray diagram for 5 centimeters, which makes it look, for me, it was at like 2 times f, but if we calculate it, for the first one, it's real. For the second one, it's virtual. Their signs are going all over the place. They're obviously using the negative version here. Oh, okay, I see. So they're getting, oh, there it is there, okay. So, what the heck? Yeah. So from the lens equation, so they get minus 10. Minus f over 2. Huh, okay. Oh, okay, that's that, okay. But they're using the minus form. Oh, and yeah, okay. So there the image is real, there's virtual, inverted upright. The magnification in the first one is minus 1, and the second one is plus 2. So that looks good. Just pay attention if you're comparing the two that we use different signs on our equation here, but you just have to know which version you're using. So this looks good. Okay. So the figure in this one is just asking which direction electrons flow in a circuit. And here we have an A, B, and here's our battery. So the electrons are flowing from the negative to the positive, so clockwise in this figure, or it's asking if it moves from A to B or B to A, so it moves from A to B. Okay, so that's just the direction of electron flow. And it's worth noting that conventional current, which was invented prior to realizing the existence of electrons, is actually in the opposite direction. So it's the opposite of electron flow, or the direction of positive flow. But electrons are obviously flowing from negative to positive. So A to B. So that looks good. Okay. Okay, so how far is the center of mass of the Earth-Moon system from the center of the Earth? And then we're given all the masses and everything. So we have our Earth, which has a mass of 5.98 times 10 to the 24 kilograms. We have a moon, which has a mass of 7.36 times 10 to the 22 kilograms. And we have the radius of the orbit, which is given as 3.84 times 10 to the 8 meters. And then it wants us to express the answer as a fraction of the Earth's radius. So first of all, our center of mass is just equal to the sum over our masses times the individual radii over the sum of our masses. Taking the Earth as our origin, or the center of the Earth as our origin, and placing all the mass there, we would have we would have 5.98 times 10 to the 24 kilograms times 0 plus 7.36 times 10 to the 22 kilograms. I've just realized that I'm not going to be able to write that much, so I'm going to actually just erase this and shift it down. So 5.98, 10 to the 24, times 0 because it's at the origin, ten to the 22 kilograms times this 3.84 times 10 to the 8 meters. And then that's all divided by the sum of the masses, so 5.98 times 10 to the 24 plus 7.36 times 10 to the 22. And so we can run this through on our calculator. This term is obviously going to 0. And so our center of mass is equal to 4.669 times 10 to the 6 meters. Okay, and now for B here, the radius of Earth is 6.371 times 10 to the 6 meters. So our center of mass over the radius of Earth is 4.669 times 10 to the 6 over 6.371 times 10 to the 6, which comes out to be 0.733. So the center of mass is about 3/4 the radius of the Earth, or the center of mass of the Moon-Earth system is actually inside the Earth because the Earth is so much more massive than the Moon. Okay, so let's check through the solutions here. Given our values, so we can solve for our center of mass, setting the Earth at the center. So it's just going to be 0 plus our moon distance and mass over the total mass, which that looks good. So about 4.67. So that looks good. And then taking the ratio, we get about 0.733, which looks good there too. So that looks correct. Okay. And all right, so you are standing on a train station platform as a train goes by close to you. So we got a dude, and we got a train flying by here, which is just gonna look like this. And it has a whistle. And I'm gonna draw something to make it more wheelie. All right, there we go. Okay. So as the train approaches, we've got a frequency of 92 hertz. So train approaches. And we've got another frequency as the train recedes. And then we've got a speed of sound of 340 meters per second. So it wants us to find the value of the actual train frequency. Okay, so the frequency heard by an observer is the speed of the wave plus the speed of the observer over the speed of the wave plus the speed of the source times the actual source frequency. And so in this case, our observer is not moving. As the train approaches us, then our F1 is just going to be 340 meters per second over 340 meters per second minus the speed of the source. So it's approaching us, so we subtract the source speed, as that appears to reduce the speed of the wave. And then as it recedes, it's going to increase the apparent speed of the wave. So it'll be a plus. So now we can figure out the speed of our source by taking our two equations. So if we do 1 divided by 2, then we're going to cancel out the source frequency and be left with this expression. And our frequencies, we can use our frequencies given. So that will be 92 over 79. Which equals 1.1646. And so that equals 340 plus Vs over 340 minus Vs. Rearranging this expression and solving for Vs, so we would have 340 plus Vs is equal to, so multiplying this to the other side, 395.9494 minus 1.1646 Vs. So now moving that to the other, so swapping, and so we have Vs on both sides, or on one side, sorry. is equal to 55.949. And these should be in meters per second still. And so then dividing and solving for Vs, V source is 25.85 meters per second. And now we can use either of our equations to solve for our source frequency. So F1 is 340 over 340 minus this 25.85 times the source frequency, or rearranging this here, so 314.15 meters per second over 340 times our F1, which is 92 hertz, is our source frequency. So our source frequency is 85 hertz. So just running through this through our calculator. So that's the numeric value of the train whistle's frequency. Okay, so looking through this here, so we have, there's our first equation, there's our second equation. We can rearrange to solve for our source speed, which is a little different. I don't know why. 2.164, 55.76, 395.76. I don't know where that comes from. 1.164. Looks like some kind of calculator error. I don't know which side it's on. But regardless, in the end it comes out to be the same, 85 hertz. So, okay. So whatever it is, it apparently worked itself out, or the decimal places just don't matter. 314, yeah, weird. Okay, well, whatever. I guess the decimal places just didn't matter. It must have been some kind of rounding error there or something. So 85 hertz, so that looks good. Okay. Now, okay, so here we're going to consider an object on an incline where friction is present. So we got an incline. The angle is theta. There's our object. And it has a coefficient of kinetic friction. And remember, our frictional force is that coefficient times the normal, where our normal always acts perpendicular to the surface. And will be equal to our projected mass force. And it actually wants us to use this as our positive x direction. And then solve for A. So we're assuming it's sliding down, so our frictional force will act this way. And so we just need the components of our gravitational forces, but in the appropriate directions. So if we look at this triangle here, I'm going to put it here actually. So we've got this. Okay, and so that is our mg, where g is our gravitational acceleration, and m is the mass of our object. then this is going to be our theta, which makes this mg cos theta, and this mg sine theta. You can kind of see it because if you flip it up and move it over, it's going to be an identical triangle to the one here. Okay, so so this, right, is our mg cos theta, and this is our mg sine theta. So putting proper direction on here, right? So this acts in the negative y direction, and it's the only force acting in our negative y direction, taking the incline as our positive x. So that means that in our fy direction, we have our normal minus mg cos theta equals 0, as it's not moving up or down. So our normal force is equal to mg cos theta. All right. So that solves for our normal. And now in the x direction, taking down the slope is positive, mg sine theta is our gravitational force, and then we're going to subtract our friction, and it equals ma. So there's our acceleration. Placing in values for our frictional force that we've solved for. So mg sine theta minus our kinetic coefficient of friction times our normal, which is mg cos theta, is equal to ma. We can remove m from several places, and we can also pull g out of this expression, and I'm just going to swap which side of the equation a is on, just because we need to solve for a. So our a is g sine theta minus mu k cos theta. And so there's our expression for the acceleration of the object. Notice it doesn't depend on mass at all. It purely just depends on the coefficient of friction and the angle of the incline. And that's it. Okay, let's look at the solution here. Body of mass m. The weight of the body vertically downwards, the normal perpendicular to the plane, force of friction upwards. So we can get mg cos theta and mg sine theta. Okay, that's not a complete solution, so we can easily get our acceleration by just considering our forces. So this solution is not complete. It does describe some of the stuff I did, but it doesn't in any way solve the question. So I'm just going to say that's incorrect. Okay. When a wave created by a certain source travels from one medium into another, how is the variation of wavelength, frequency, and velocity? So the easiest way to think about this is light, but it does function for every other source. But if we consider light traveling from one medium into another, then the speed, well, the biggest takeaway here is that our frequencies will always be the same. So I'm just going to put F naught actually. So the frequency doesn't change, and so that basically answers the entire question, because our frequencies are always held fixed. Our speeds in any medium is going to be whatever the zero speed is over the index. Again, this is for light, but similar expressions can be derived for sound waves, or for any electromagnetic wave, I should say, is this expression. So our V1 is that, whereas our V2 is V naught over N2. And because we know there's a relation, so our speeds are dropping depending on the index. And because we know that the velocity of a wave is the frequency times the wavelength, that means that our wavelength is the frequency over our the wavelength is the speed over our frequency. Frequency is not changing, but our speed is changing. So that means that as speed is getting lower, our wavelength is also decreasing. So we get an apparent wavelength shift, but frequency is always maintained. When a wave created by a certain source travels from a medium into another, the velocity and the wavelength vary, but the frequency remains the same. When we travel to a denser medium, its velocity increases. And the wavelength decreases. Did I do that fine? No, yeah. B equals F lambda. Oh, when a wave travels from a denser medium to a rarer. Yeah, okay, that makes more sense. Right, okay. So yeah, if V2 is greater than V1, then lambda is actually going to, yeah, okay. Its velocity increases and the wavelength decreases. From a rare to a denser, the velocity of the wave decreases and the wavelength increases. Okay, so that looks good. So the takeaway here is frequency. That's the one that I remember, is frequency just doesn't change. And because the relation between speed, frequency, and wavelength, that means that the other two have to change. So that looks good. Okay. All right, so here we have a bit of a lengthy one, but okay. So we've got a salad spinner that a cook gets up to an angular speed of 20 revolutions in 5 seconds, or our omega is 20 times 2 pi over 5 seconds, which is equal to 8 pi per second. And then he stops spinning it, and it slows down at a constant angular speed, and it rotates 6 more times. So our delta theta after stopping it is 6 revolutions, which is equal to 6 times 2 pi radians, or 12 pi. And it asks, what is the magnitude of the angular acceleration? Okay, so if our angular acceleration is constant, then this equals our d omega by dt. And we can solve for omega by integrating these expressions from omega naught to omega I, from 0 to t. So from omega naught to omega. So omega is alpha t minus omega naught. And then we can get our theta expression similarly. So theta, omega is d theta by dt. So d theta is equal to omega dt. Or if we integrate from theta naught to theta, and integrate from 0 to t, then we would get theta minus theta naught is equal to alpha t minus omega naught integral dt, which is equal to 1/2 alpha t squared minus omega naught t. Minus omega naught t. There we go. Okay. So this, on this side, I've left it like this because this is our delta theta. And so we can solve for our time here in terms of our alpha. As we know, our delta theta is 12 pi. And that equals 1/2 alpha t squared minus our omega naught, which is 8 pi per second. Okay. So rearranging this, we would have 0 is 1/2 alpha t squared minus 8 pi per second. Why is that minus? Oh, that should be plus, sorry. Twink. Yeah, this should have been plus up here. My apologies. So this should be plus and plus. There we go. And minus 12 pi. Okay, so then our t is minus 8 pi plus or minus square root of 8 pi squared minus 4 times 1/2 alpha times 12 pi, all square rooted, over 2a, so just alpha. And so we can't really solve this because we don't know what alpha is, but we can make some simplifications here. So I'm going to take out 8 squared. And so this will be minus, or I'm going to take out the 8 pi completely, minus 1 plus or minus square root of 1 minus, and then if we take out the 8 pi from here, then this is, or 8 pi squared I should say, then this is 3/8, and pi on the bottom, alpha 1/2 squared are the units. And this should be 1/2. And no, it shouldn't. My apologies. But this, oh yeah, there we go. So this is all divided by, or this is divided by alpha. So I'll just put it there. And so this alpha will cancel with this per second squared, making that unitless. The 1 will be unitless, and this will actually be, yeah, okay. So that looks good. And now time can't be negative, so the plus, so the plus solution is the only one here that matters. So our time is 8 pi over alpha. Oh yeah, this should be per seconds. What am I doing? There we go. Times, and so the 1 over seconds divided by the 1 over seconds squared will give us seconds. So square root 1 minus 3 over 8 pi alpha per second squared minus 1. So that's our time. Okay. And so then going back to our omega expression, we have that alpha times time is omega f minus omega naught, as we had that omega is alpha t plus omega naught. And so we can solve for our alpha with this expression. And so we know that omega f is 0, and we know that omega naught is 8 pi per seconds. So that means that alpha times our time (1 minus 3 over 8 pi alpha per second squared minus 1 is equal to minus 8 pi per seconds. So our alpha actually cancels here, and then we can divide by our 8 pi. So we get root 1 minus 3 over 8 pi alpha per second squared minus 1 is equal to minus 1 over seconds. So dividing by this 8 pi, we can now add 1, and that will actually cancel the per seconds on this side as well, because we've got our per second there. So now we can add 1, giving us square root of 1 minus 3 over 8 pi alpha equals 0. Square both sides, so then we get 1 minus 3 over 8 pi. Oh, I made a whole bunch of mistakes, because this should have been a minus sign there, meaning that's plus, meaning that's plus, meaning that's plus, 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 plus. There we go. Square both sides. And then rearranging this now for alpha, we have that alpha, yeah, I messed up the units there too, so that should just have been seconds squared the whole time. So then alpha is minus 8 pi over 3 per second squared. So it was a little messy there. And I messed up a couple of units. But that's the answer that it comes out to be. So yeah, so I messed up a couple of units and a couple signs, but that shows why you need to pay attention closely when you're running through things. But there's our angular acceleration that the spinner is slowing down at. Now if we run through this solution here, they did it a significantly easier way. So there's our initial velocity, which is our 8 pi per seconds. Our final is 0. And so instead we could have just used that omega squared is omega naught squared minus 2 alpha delta theta. And just plugged in our values, which would have given us our 8 pi over 3. But the negative sign would be wrong. Yeah, there'd be no negative sign. Interesting. But in any case, that looks good. And if anything, I showed how possible it is to have errors if you're not paying close attention. Okay, so that looks good. And I'm actually going to stop it there and say I hope you enjoyed this session. If you did, please subscribe. If you want to leave questions, follow the links below the video. This has been Jeff Krause for OneClass.